Okay, so this is day 2 on exponential growth and decay function, 7.1. Today we're focusing in on exponential decay. Yesterday we did exponential growth. And this is the form that we use in exponential growth or decay. Y equals a times b to the power of x minus h plus k. And we should already know that the a value tells you if it opens up or down. And yesterday we did growth functions, and as you could see, the a value here is positive 1, right? The b is 2, but the a value is positive 1 because there is no number that's being multiplied out in the front. So because it's positive 1, it is opening up, it's growing up. Down here, we saw that the a value is technically negative 1. As a matter of fact, when we did this problem, we made sure to rewrite this not as negative 2, but as negative 1 times 2. So the a value is negative 1, and that's why it's opening down. Okay, it's growing down in the negative direction. So the a value tells you if it opens up or down. Let's go back to the notes here. What else? The b value is very, very important. That b value there is going to tell you if you actually have a growth function or a decay function. All right? If your b value is a value greater than 1, it's going to be a growth function. If your b value is a value between 0 and 1, as in a fraction or a decimal like 0.99 or 1/4 or 3/4 or 9/10, any fraction that's less than 1 is going to cause it to decay instead of grow. And that makes total sense because if you take any number you want, give me any number. 7. If you take 7 and multiply it by a value that's greater than 1, it's going to grow. The 7 is going to grow. If you take 7 and multiply it by a fraction that's less than 1, it's going to decay, it's going to shrink, it's going to be less than 7. So this b value is very important. It'll tell you if you have a growth function or a decay function. And we already know that h is always with x. You have to think opposite of what you see because of that minus sign. K is always being added or subtracted at the very end. Not only that, the k value also tells you your asymptote. What is an asymptote? It's the line, in this case, the horizontal line that your graph will infinitely approach but never actually touch. So those are all good notes that you guys should jot down, whether you do it off the sideboard right there or off of this video later. You can do that later. Let's move on to these notes right here. We just said an asymptote is a line that your graph will infinitely approach but never touch. It'll infinitely approach it but never touch it. Now, there's a couple more facts down here. It says growth functions from left to right grow away from the asymptote. Listen to that, guys. Growth functions from left to right grow away from the asymptote. Growth functions from left to right will grow away from the asymptote. Now, we already saw growth functions yesterday. And if you take a look at any of these growth functions from left to right, what's happening? It's growing away from the asymptote. Here's your asymptote. It's growing away from your asymptote. Got that? Even down here, from left to right, it's growing away from that asymptote. Make sense? So growth functions from left to right grow away from asymptotes. Decay functions. Now, what do I mean by decay functions? If that b is like a decimal like 0.9 or a fraction like 3/4, if it's something less than 1, then it's a decay function. Decay functions from left to right decay towards the asymptote. Decay towards the asymptote. So we haven't looked at a decay function yet, but let's say I had a decay function. It's going to start off as a huge y value somewhere up here, and it's going to decay towards that asymptote, infinitely approaching but never touching. Does that make sense? So a growth function from left to right will grow away from the asymptote. A decay function from left to right is going to decay towards that asymptote from left to right. Okay? So I hope we're understanding that. Let's go back to our notes here. And these steps on graphing, we're going to hold off on that right now. Let's see if you guys understand the growth factor and being able to determine when it's actually growth and when it's actually decay. So let me move these notes to the side. ladies and gentlemen, I need you to determine which are growth and which are decay functions. Let me throw in maybe one more. Let's do a number 5. Y is equal to, give me any number you want. 4. And then we're going to put 0.89 in there, and then to the x minus 13 plus 72, whatever. So on this first one, ladies and gentlemen, is this a growth or a decay function?
Growth.
It's a growth function. Why is it a growth function?
Because it's more than 1.
The b value is greater than 1. Some of you think, oh, it's a fraction, it's a decay. No, what is 4 divided by 3? It's 1 point something. It's greater than 1. So that's definitely going to be a growth function. From left to right, it's going to grow away from the asymptote. As a matter of fact, check this out. For funsies, I could actually do a quick sketch of this first one that you guys told me it was a growth function. What do we know about growth functions? From left to right, it grows away from the asymptote. Where's the asymptote? What is the asymptote of this one that you don't even see yet? What's the asymptote? The asymptote is y equals, you said it? 3. Y equals 3. So if you go to the y value of 3 and you do a horizontal line right through it, this is your asymptote. And what do we know about growth functions? From left to right, what do? They grow away from the asymptote. So a quick sketch that's very accurate would look like this. It looks like it's on the asymptote and then it grows away from the asymptote. I mean, just by knowing those facts, you'll be able to select the correct answer on a multiple choice test. It's pretty cool. So anyway, let's go back. How about number 2? Is that a growth or a decay function? Decay. Why is it a decay? Because it's less than 1, right? Okay. And if I wanted to do a sketch, we're not supposed to do sketches here, but just for funsies, if I wanted to do a sketch, what's my asymptote going to be on number 2? 7, right? So let's go to 7. 1, 2, 3, 4, 5, 6, 7. Let's do our asymptote right there at 7. And it is decaying towards the asymptote from left to right. So that would mean that it's going to start off at some huge value, especially because of that 99, but it's going to decay towards that asymptote. Does that make sense? Now, I'm not even asking you to sketch it. I just need you to say whether it's a decay or growth based on that b value, the growth or the decay factor. Anyway, let's move on to number 3. Is that a growth or a decay function? Decay. It's less than 1. The b is less than 1, so it's a decay function. How about number 4? Is this a growth or a decay function? So number 4, some people get confused because of the minus sign. We need to remember the notes. Whoops. The notes, you need to write it so you could identify the a value and identify your true b value. So when we look at that right here, you're going to have to rewrite this guy, or at least visualize it as y equals -1 as your a value times 2 to the x plus 5. And now look at that b value. Is that a growth or a decay? Definitely growth, all right? So how about that last one, growth or decay? Decay. 0.89 is less than 1. So just to review, the first one was growth because the b value is greater than 1. This is a decay because the b value is less than 1. This is a decay because the b value is less than 1. This is a growth because the b value is really 2, which is greater than 1, which is growing. This one's a decay because that's a decimal less than 1. So I think that's a good skill that you guys have acquired, I hope, being able to determine if it's a growth or a decay function, just algebraically understanding the growth or the decay factor, the b. But you also need to be able to look at a graph visually and determine also if it's a growth or a decay function. So let's move these to the side, and we have several graphs here. Number 1, so right here what I'm really testing is, do you understand that growth functions from left to right grow away from the asymptote? And I'm also wanting you to understand that decay functions from left to right decay towards the asymptote, right? So let's see if we understand that. Is this a growth or a decay function? Definitely growth, because from left to right, it grows away from this asymptote. What's the asymptote, by the way? Negative 3. That means your k value of your actual function will be negative 3. So this is definitely a growth function. Okay, how about this next one? Is that a growth or a decay? Decay. I hope you see that, because from left to right, it decays towards the asymptote of y equals 1. Okay? It never actually touches y equals 1. It infinitely approaches y equals 1. How about this one? A growth or a decay? Some people are it's growing, it's getting bigger, right? No, it's not a growth. Is it infinitely growing away from the asymptote or decaying towards the asymptote? Decaying towards the asymptote. Now, some of us are thinking, how could it be a decay if it's getting bigger, right? Hold on a second. My bad. So how could it be a decay if it's getting bigger? Well, the thing is, it's like if you had a large amount of credit card debt and you decayed that debt and you made it level off, right? So that's a decay function. So anyway, decay. How about this guy? Growth or decay? That's also a decay. Why? Because from left to right, what's happening? It's decaying towards the asymptote, which is y equals 4. A growth function will grow away from the asymptote from left to right. Okay? So how about number 5 right here? Is this a growth or a decay? Growth, because from left to right, it grows away from the asymptote y equals 4. Is this a growth or a decay? Growth. Why? Because it grows away from the asymptote y equals 0. How about this guy? Growth or decay? This is also a growth. Why is it a growth? Because it grows away from y equals 0, from the x-axis. How about this guy? Is it a growth or a decay? It's also a growth. Why? Because from left to right, it grows away from the asymptote y equals negative 1. Got it? I hope so. You need to get it. Let's get to the actual graphing portion of today. So we are at this portion of our notes. It tells us steps to graphing exponential growth or decay functions. And we're tackling this like the way we would any other square root function or even a parabola. You could identify h and k but ignore them. So I say step 1, box in the function y equals a b to the x. Step 2, make an xy table with consecutive integer inputs and plug in 0 to find its output. So step 2 is to make this xy table with nice, beautiful numbers that are in order, right? And it says plug in 0 and get an output. Now from there, use the growth or the decay factor, which is your b value. Use the growth or the decay factor to get from this output, that single output that you got by plugging in 0, you got an output. Use that growth or the decay to get to your other outputs. So if for some reason this would have been a 4 and this is a decay of 1/2, you're going to go 4 times half, you'll get 2. 2 times half, you'll get 1. Does that make sense? If this were a 2 or a 3, let's say it were a 3 and this value was a 5. If this was a 3 and this is a 5, you'd have to multiply by 3 to get 15, multiply by 3 to get 45, and so on and so on. I guess the best way to understand these steps is to see them in action. But before we see them in action, the last thing after you get all your coordinates is to shift them according to your h and k, because after all, we got the coordinates of this parent graph ignoring h and k. At the end, we have to actually consider h and k and move all the coordinates. So again, you could write these notes right off the board, or you could pause this video later and write them down later from home. Right now, I want to look at this last one. Let's jump to that last one. I guess that's as challenging as it could get, right? Step 1 says box in the function y equals a b to the x, ignoring h and k. So I'm going to do that. What is my h, by the way? Negative 1. You think opposite of what you see. The k value is? Negative 3. So ultimately what that means, negative 1 means you're going to shift your coordinates 1 to the left, and k means you're going to shift them 3 down, okay? So that was step 1. Step 2 says make an xy table with those consecutive integer inputs and plug in 0 to find its output. All right, so let's do that. Step 2, xy table, consecutive integer inputs, -3, -2, -1, 0, 1, 2, 3, and plug in 0. It's super easy. I say plug in 0. You can plug in any number you want, but I say plug in 0 because when you do the power of 0, anything to the power of 0 is what? 1, and 1 times 3 is what? 3. So when you plug in 0, you get out a 3. Now, what does it say in our notes after that? So far, those 2 steps have been ridiculously easy, right? Let's look at the rest of the notes here. Number 3, use the growth or the decay factor B to find other outputs and then shift your coordinates according to H and K. So let's use the growth or the decay factor. First of all, is this a growth or a decay? It's a decay. How do I know that? Because it's 1/2. It's less than 1. So I'm going to need to decay this output by that 1/2 to get to my next one. So this gets a little ugly because we end up with 3 times half. What's half of 3? What's half of $3? $1.50, right? 1.5, right? So do you see how I decayed the output just by multiplying by that 1/2? 3 times 1/2 is 1.5. And then I need to decay this further by 1/2 to get to the next one. So what's half of $1.50? 0.75, right? 0.75. And then half of that is, it's getting ugly. Half of 75 cents is 0.375, I think. I don't know, but you get the idea that as you're going this way, it's going to get smaller and smaller because you're going to take half of that, half of that, half of that. It keeps getting smaller and smaller and smaller, infinitely approaching nothing because we're not even mentioning the K value, which is the asymptote. Right now, we're just pretending that it was this boxed-in function. So anyways, if from here to here, I divided by the decay factor or multiplied by the decay factor 1/2, which is like dividing by 2, dividing by 2, dividing by 2, backwards would be what? Instead of multiplying by half, it's multiplying by the reciprocal, which is what? 2. That makes total sense, right? From here to here, half of it's 1.5. From here to here, you multiply by 2 to get to 3. So what's this next one going to be up here? 6. And then 12. And then 24, which is off the graph. Pointless to even do that one because it's off the graph. So let's plot the nice points. 0, 3, 1, 2, 3. Put that dot right there. 1, 1.5. 1, 1.5, 2.75, 1, 2, it's not even 1. 0.75 is a little more than half, but definitely less than 1. And then 3 and 0.3, you guys get the idea. What's happening here? It's decaying, and it's going to infinitely decay towards 0 on the parent graph, on the boxed-in function. So you could put some dots if you wanted to, but this is not even our end graph. By the way, let's go in the other direction. Let's plug or plot -1, 6, -1, 1, 2, 3, 4, 5, 6, and -2, 12 is off the graph. So I don't even have to put it. But anyway, there's our graph. What do I need to do to these coordinates to get my final graph? Shift them. Shift them where? According to H and K. 1 to the left, 3 down. And you know what? Even before shifting, a great idea would be to identify your actual asymptote. What is the asymptote? Y equals what? -3. So if I go to y equals -1, 2, 3, and I draw a dotted line right there, I already know that this decay function from left to right has to infinitely approach it. So I know that my end graph is going to be on this asymptote going that way. Okay, let's shift all these coordinates, 1 to the left and 3 down. So 1, 1, 2, 3 right there. And this one, 1, 1, 2, 3 right there at the origin. Oh, no, that's not at the origin. Sorry. And then the other one, down, 1, 2, 3. So this one's kind of confusing because you're at the halfway, 1 this way, and then 1 at that halfway, 2, 3, it'd be right there. And we know that it's approaching that asymptote. So you could just draw it right there. You don't need all those coordinates. Put an arrow right here on this way. And that's your end product right there. Let's finish off this video by answering some questions with regards to this decay function. How about the domain and range? What would the domain be? Does this blue graph go to the left forever? Yes, even though it goes up, it continues to go up and to the left. Does it go to the right forever? Yes. So the domain, it has x values being all real numbers because it does go to the left and to the right forever. How about the range? The range of this guy. Where is this entire graph at? Does it go up and down forever? No. Like, yeah, it does not exist down here at -10. Actually, it doesn't even exist at -3. right? I mean, it looks like it touches -3, but we know that it never actually touches, it just infinitely approaches. But this entire blue graph is above the y value of -3. So the range would be y is above the y value of -3. So there's your range. We could also even do end behavior notation. We could say as x approaches -infinity, what happens as x approaches -infinity? What happens as you go to the right? What happens? Y goes to positive infinity, right? So you could say that y goes to positive infinity because as you go to the right, it goes up, okay? And then we're going to say as x approaches positive infinity, what happens? As x approaches positive infinity, where is that y value approaching? Y value approaches what? Say again? -3. It approaches -3, right? As you're going this way, it's approaching forever that y value of -3, that asymptote of -3. Good stuff. So I think with this lesson, you should be able to graph. This is really easy. There's no h and k. You don't have to shift anything. Same thing here. You don't have to shift anything. On this one, you do have to shift. But go ahead and try those. Ask me questions if you need help, and we'll continue this tomorrow.